Hello everyone, welcome to my class of Engineering Mathematics. So today we are going to study about differential equations. Differential is a word derived from differentiation. A differential equation is the one where the derivatives of the dependent variable and the independent variable occur together, and a relationship between them is expressed in a general differential equation format. To understand this better, let us take an example. How far is your college from your home? Let me just take this distance as 20 kilometers. So how much time do you actually take to travel from your college to your home? Let me take it as 4 hours, suppose. Since we know velocity, which is a vector quantity and is expressed as v is equals to change in distance divided by change in time. Now, if we take s representing the distance, small t representing as time, then v can be expressed as delta s upon delta t, where v is known as the vector velocity. Now, if the time t tends to 0, then this equation delta s upon delta t can be expressed as ds upon dt. For a very small change in time delta t tending to 0, the equation delta s upon delta t will be called as ds upon dt. So v is equals to ds upon dt is a very simple form of a differential equation. Similarly, there is another form of differential equation, a is equals to dv by dt. So you have already dealt with these equations ever since you started studying about speed, distance and time in your 6th, 7th, 8th, 9th and 10th standards. Also, do you remember the Newton's equation of motion? V is equals to u plus at is actually a form of a differential equation, or we can express Newton's equation of motion in the form of differential equation. How? Let me show you. V is equals to u plus at. If we bring u to the other side, it becomes v minus u upon delta t is equals to a, where a is a constant acceleration. Now v minus u upon delta t can also be written as delta v upon delta t, that is change in velocity divided by change in time. Again, if delta t tends to 0, that is the change in time is reduced to a very small quantity, then it can be represented as dv by dt. What is this? This is actually a differential equation. So, while reading about differential equations in your course book, you must have come across the words degree and order of a differential equation. What is meant by degree and order of a differential equation? First, we will define what is meant by order. Order is defined as the order of a highest order derivative term of a differential equation. Degree is the power of the highest order derivatives in the differential equation. But, the equation must be free from radicals and fractions as far as the derivatives are concerned. Since you may not have understood the meaning of degree and order, let us try to understand these things from examples. To understand, let's take 3 examples. Example number 1. d2x by dt square plus 2 times x cube is equals to 0. In this, there is only one derivative term, which is d2x upon dt square. So, the order of this equation will be 2. And degree will be the power of the highest order derivative term, which is only d2x upon dt square, which is going to be 1. In example number 2, 3 times d2y by dt square plus dy by dt the whole cube plus y square plus 2 is equals to x. Since there are 2 derivative terms in this question, first is d2y by dt square, second one being dy by dt. So the highest order derivative term naturally is d2y by dt square. So the order of this differential equation is 2. Now the power of the highest order derivative is 1. So the degree of this differential equation will be 1. In example number 3, d cube y by dx cube plus 4 times of under root of dy by dx the whole cube plus y square is equals to 0. Since in this equation there are two derivatives, that is d cube y by dx cube and dy by dx. Naturally, the second derivative term is under a fraction, that is a square root. So to free this equation from radicals and fractions, let us first transform this equation free from radicals and fractions. First bringing the term 4 times under root of dy by dx the whole cube plus y square to the right and then squaring both sides. We get d cube y by dx cube the whole square is equals to 16 times bracket dy by dx the whole cube plus y square. So now the highest order derivative terms in this equation is d cube y by dx cube. So the order of this differential equation will be 3 and the degree will be 2. d cube y by. So now coming back to the important topic of linear differential equations of nth order. Assuming that you all are aware about differential equations now and the terms order and degree from the previous lectures, so today we will be studying about linear differential equations. What is a linear differential equation? What do you mean by linear differential equation with constant coefficients? What is the meaning of CF and PI which we find in the general solution of linear differential equations? What are the rules for finding out the complementary function? What are the rules for finding out the particular integral? How to solve questions related to linear differential equations? Let us start with the question, what is a linear differential equation? A linear differential equation is the one in which the dependent variable and its derivatives occur only in the first degree and are not multiplied together. So the general linear differential equation of nth order is of the form dny by dx ki power n plus p1 dn minus y by dx ki power n minus 1 plus p2 dn minus 2y dx ki power n minus 2 plus pny is equals to fx. dny by dx ki power n, this is a derivative of the dependent variable y. p1, p2, p3 are functions of independent variable x. Type 2. dny by dx ki power n plus k1 dn minus 1 by dx ki power n minus 1 plus k2 dn minus 2y by dx ki power n minus 2 up till kny is equals to fx is another form of a linear differential equation where k1, k2, k3 up till kn are all constant and fx is a visible function of x. Since you can see in this general format of differential equation, the independent variable is x and the dependent variable is y. There is no term in between the plus or minus signs where the dependent variable and the derivative are multiplied. So such an equation is known as a linear differential equation. To solve any linear differential equation, the complete solution is defined by y is equals to CF plus PI. CF is called the complementary function. PI is called the particular integral. In the next modules, we will be studying about the numerous methods to find out complementary function and particular integral. While solving a linear differential equation, we first find out the roots of the equation. According to the numerous ways in which the roots might be found out, there are different rules for finding the complementary function which is visible in this table. When the roots are real and different, then CF is defined as C1 e power m1x plus C2 e power m2x. When there is a pair of real and equal roots, then the complementary function is defined as C1 plus C2x whole into e power m1x. When the roots are real and they are also equal, then in that case, the CF will be defined as C1 plus C2x plus C3x square e to the power m1x, where there are 3 roots. When there is a pair of imaginary roots like alpha plus I beta and alpha minus I beta, then the complementary function is defined as C1 cos beta x plus C2 sin beta x whole into e power alpha x. When there are 2 pairs of equal and imaginary roots as alpha plus minus I beta, alpha plus minus I beta both equal and imaginary pairs, then the complementary function is defined as e power alpha x whole bracket C1 plus C2x cos beta x plus C3 plus C4x sin beta x. To understand how to find the complementary function, let us take an example of a second order linear differential equation. Example number 1. d2y by dx square plus y is equals to 0. Let us represent dy by dx as d. So d2y by dx square can be written as capital D's whole square plus 1 is equals to 0. So the roots are plus minus I, which is a pair of imaginary roots. So the complementary function can be written as C1 cos beta x plus C2 sin beta x e to the power alpha x. Here beta is equals to plus minus 1, alpha is equals to 0. Putting in the values, we get CF is equals to C1 cos x plus C2 sin x. Since the right hand side of this equation is equals to 0, so Pi for time being until we study about Pi in the next modules will be taken as 0. So the complete solution of this differential equation can be represented as y is equals to Cf plus Pi. Y is equals to C1 cos x plus C2 sin x. This is called the general solution of a differential equation. It is known as general solution because the values of C1 and C2 can be found out by putting in the conditions which are given in the question, which we will see in the later examples. Example number 2. Y double dash to plus 2 times y dash plus y is equals to 0. The boundary conditions given are y0 is equals to 0, y1 is equals to 0. Now the questioner is asking what is y 0.5. Expressing the equation in the form of d square plus 2d plus y is equals to 0, we can express it as d plus 1 the whole square is equals to 0. Roots of this equation are minus 1, minus 1, which are real and equal roots. Now using the equation y is equals to Cf plus Pi, where Cf is equals to C1 plus C2x e to the power alpha x, because these are a pair of real and equal roots. So the general solution is C1 plus C2x e to the power minus x. Putting the boundary condition y0 is equals to 0, we get C1 is equals to 0. Again putting the second boundary condition y1 is equals to 0, we get C2 is equals to 0. So the general solution of this equation can be expressed as y is equals to C1 plus C2x e to the power minus x. Y is equals to 0 is the solution of the given linear differential equation. Since the question has been asking about the value of y 0.5, so the answer to this question y 0.5 is 0. Example number 3. Find the solution of d2y by dx square plus 2 times dy by dx plus 17y is equals to 0. Given condition is y0 is equals to 1, dy by dx pi by 4 is equals to 0 in the range x belonging to 0 to pi by 4 is given by. To find the solution, let us first write the equation in the form of d square plus 2d plus 17 whole y is equals to 0. The root of this equation are d is equals to minus 1 plus minus 4i, which is an imaginary pair. If we express this as alpha plus minus I beta, so the value of alpha comes out to be minus 1 and beta is equals to 4. So the complementary function CF for this equation can be expressed as C1 cos beta x plus C2 sin beta x whole into e to the power alpha x. Putting in the value of alpha is equals to minus 1 and beta is equals to 4, we get CF is equals to C1 cos 4x plus C2 sin 4x whole into e to the power minus x. Now putting in the boundary condition y0 is equals to 1, we get C1 is equals to 1. To find the second boundary condition, we will have to take out the differential value dy by dx. The differential value dy by dx and then putting the value of x is equals to pi by 4 as the following solution, we get C2 is equals to 1 by 4. Now putting in the value of C1 and C2 in the general solution of y is equals to CF plus PI, where PI will be equal to 0 since the RHS of the differential equation is 0. Putting in the value of complementary function and putting in C1 and C2 values in the general solution, we get y is equals to e to the power minus x cos 4x plus 1 by 4 sin 4x. This is called the complete solution of the differential equation.